So good morning, good afternoon, and good evening, everyone from all around the globe. My name is Eric Mail, and I'll be helping moderate today's webinar on single instruction, multiple data, SIMD, in Julia. Today, you'll learn how recent processor architecture advancements can now execute the same instruction, like additions, across multiple data points simultaneously, or on even larger batches within one instruction. Julia has many ways to take advantage of SIMD's performance for this code optimization. We'd like to have this an interactive session today, so please write your questions in the chat, and we'll either address them on the fly or address each question individually following the demonstration. With that said, I'd like to introduce you to today's presenter, Christopher Carlson. Christopher is a senior software engineer at Julia Computing, is a longtime contributor to the Julia language, specifically managing and debugging the 1000 star plus package compiler.jl. He received his Master's of Science in Applied Mathematics from Chalmers University of Technology in Gothenburg, Sweden. Please welcome Christopher Carlson.
Okay, thank you, Eric. So first, as always, checking is my screen visible and am I audible, things like that?
Audible and see the screen as well. Yeah, it looks like you're good.
Okay, so thanks, Eric, and welcome everyone to this webinar about SIMD in Julia. We call it automatic and explicit. And to start off with, let's look at what SIMD means then. Well, SIMD is an abbreviation for single instruction, multiple data. And I thought we would dig into these terms instruction and data just a little bit to get a bit of background. So if we start with data, when we're programming, we have this high-level data. We might have strings, data frames, dictionaries, sets, matrices, all kinds of things that we consider sort of data. But these are not directly acted on by the CPU or the processor. When we go lower down to a lower level and look at what the CPU actually interact with, it's pretty much numbers in the end. And all these high-level data are more abstraction that's been on top, built on top of these numbers. So typically we have integers that have different sizes, how many bits there are, they can be unsigned or signed. And we have floating point numbers that also can be of different sizes. And basically everything in the end is represented by these low level data. So if we take a string here in Julia, I just did a string called Julia here. And then here we can see how this string is represented with in the code units function. So this string Julia is actually just some numbers here, and that's sort of the core low-level representation of the string. So that's sort of what we mean when we say data here in the SIMD sense. We talk about these low-level things like integers and floats. And then when it comes to instructions, well, we have these high-level instructions, matrix multiplication, sorting, and so on. It's sort of quite high-level instruction, but in the same way as before, these are not really the things we talk about when we talk about instructions in the SIMD sense. So in the SIMD sense, we talk about this very, very low-level instruction that the CPU directly executes. So some example of these are mathematical operations like addition, multiplication, exponentials, even special functions like that. Comparison, so we can compare two numbers if they're less than, equal, and greater than, and so on. Some conversions between, for example, integers and floats. We can do bit manipulations, swap bytes, and so on like that. And then, of course, dealing with memory, so we can load from memory and store from memory. And all these high-level instructions, in the end, they boil down to executing a lot of these low-level instructions. And these low-level instructions is where these SIMD is kind of about. So the simplest possible SIMD example here I would show. So first I will show it without SIMD, just how it would be normally. So here I have, look at the Julia code first. We take in 8 numbers here, x1 to x4 and y1 to y4. Then we create a set value here, which is just a sum, and then we return it. So if you look at the figure to the right, it's a bit maybe easier to see here. We have 4 additions going on. So if we look at the number of data we have here, we have 12 numbers, and we have 4 instructions. depending on how you count it. We basically have 4 additions here, and then you could say that we have 4 assignments as well. But all of these instruction has to be fetched by the processor, it has to be decoded to figure out what it's going to do, and it has to be executed, all 4 of these. And if we look at what code is actually generated when we run this function, Julia makes it really easy. It has these introspections macros, so I can just put add code native before a function call here. And here I also turned off some debugging for you, which shows some file information if I didn't put this off. But to fit on the slide, I turned off debugging for you. And we can see that in the end, what the CPU will actually execute here is 4 addition instructions, 1 for each of these, which is natural. And then in the end, it does some move instructions to put the result in the right place. But the gist of it is that this code generates 4 instructions. So the core of SIMD then is basically that we sort of operate on a bunch of data in one instruction. So if I just group these pieces of data with some kind of a box here, I can think about that I am doing one addition within all these values and all these values, and that gives me the result of these, the result into these 4 values. So I have a Julia function here that takes 1 x and 1 y, and now we can think about these as sort of these vector or box set with values. And then I create a set here, which I do as the use the broadcasting notation here, which basically means exactly like the figure here to the right. It will take x1 plus y1, put it in z1, and it will do everything element-wise. And what I input to this function then are 2 tuples here, and we can think about the tuples as these boxes. And I look at the generated code this time. And what happens then is that we only get one instruction, one SIMD instruction, which is, if we go back and look, we have this add q here, add code word. And then if we go forward, we have this VP add q, and V here is for vectorized and P is packed. So basically what this does is that there's one instruction that will execute this whole thing at once. So in this case, we sort of have 3 pieces of data where each data is a little box here, and we have one instruction. We have this super instruction here that does the whole thing in one go. And that's sort of the core point of SIMD, is to sort of reduce the number of instructions and operate on these batches of data for every one of those instructions. So one thing we can talk about is the size or the width of a SIMD unit. So if I go back, you see the box I put here was so that 4 values would fit in them. And if each of these values are 64-bit, this would be 256 wide SIMD unit. They would need to fit 256 bits in here. Different instruction set, basically depending on which instruction is run and what instruction set the CPU supports, can fit different amount of data in these boxes. So SCC, which is quite old now, you could fit 128 bits. So that would be, for example, 2 64-bit integers or 4 float 32s, for example, 32-bit floating point numbers. Then there's AVX, which is, I would say, quite common now. It fits twice as much in there. And then there's AVX 512, which is basically not very common in common desktop CPUs or laptop CPUs. Mostly Intel server CPUs have this AVX 512. So I would say the AVX is the most common now. So if we go back to our function that executed this addition between SIMD, and we put in 8 int32 numbers in there, so that would be 256 bits. We can see here that we generate one add instruction. The compiler has generated one add instruction because it managed to fit 256 bits into one of these boxes. But if I instead just change these to int64, then all of a sudden we can't really fit it in one box anymore. So here the compiler generated 2 SIMD instruction, one for the first 256 bit and then one for the second 256 bits. So some conclusions we can draw from this is that smaller is better. So if you can use int32, for example, here. You can see that we could fit twice as much data into one SIMD register here, and we only have to do one instruction, while here we have to do two instructions. So that's a useful thing to think about when it comes to SIMD, and maybe yes, comes to the floating point, you can think about maybe you can reduce your tolerance to float 32 to only have 32-bit floating points, and then you could maybe only use half the number of instructions, and you will have the amount of memory and so on. So it's a trade-off, but it's good to know that the possibility exists. And then there's something that's worth mentioning is gathers and scatters. So one thing is that to operate on these this data, we need to put all these values into these boxes so that the SIMD instruction can operate on it. But maybe we have the data a bit spread out in memory, so we need to bring that data in memory into a box. So if this data is already contiguous in memory, like in the first case here, we just basically load that into one of these SIMD lanes. But if we have data a bit spread out here, we need to do something called a gather, which is a more general concept in a load, where we basically take data with some stride, for example, or we could put some kind of index. Anyway, we need to bring in the data into a SIMD unit. And the opposite of that, it's scatter. When we have done operations with these, we need to store them back into memory again. And there's many different versions of this. You can have different strides here. You can have arbitrary indices. You can do masking, which means that you only load some values and some other are undetermined and so on. But basically, you need ways to get things into your SIMD registers and then store them back into memory. And if your data is all spread out, it can be the case that it's the majority of the time is to actually bring the data into these SIMD registers, and that might end up being that the SIMD code turns out to be slower than the scalar code or the normal code. So that's always worth thinking about how things are stored in memory. And generally, you want to store things in the same way they're going to be accessed and operated on, instead of storing things all over the place, and then you have to sort of bring it back in and then store it back out again. So generally, when working with SIMD, it's quite important to think about how data is actually laid out in memory. And just to mention it, there are many other sort of fancy instructions than just additions and multiplication and so on. So there are instructions for doing AES decryption. There are instructions that do string comparison. There are even like statistics instructions that compute like CDFs and so on. I'm not sure how frequently these are used, but it's interesting to know they exist. And the availability of these things might depend on which CPU you have. But it's interesting to know that the CPUs are not only executing very simple additions, they also can do quite advanced stuff in, yeah. So why would we care about SIMD? And I would say the one-word answer is performance. So if we want to make it really short and not go into details, one of the SIMD instructions that act on, for example, 4 values is not 4 times as expensive as the scalar version acting on one value. So in fact, SIMD instructions can have the same cost as the scalar version. Basically, it costs the same to do one scalar instruction, do A plus B, as it would do to do the SIMD version where you do 4 additions at once. So just as an example here, I wrote a sum function that does have SIMD and a sum function that don't have it. I'm not putting up the definitions here, but then I just timed them. And you can see the SIMD instruction is about 3 times faster here. So that's sort of why we want to care about SIMD, is because of performance. So how do we see if the code we are running is actually using SIMD then? Well, as I showed before, Julia has some nice code introspection tools. So if I have a sum function here, and you do code LLVM with it, and I give it a tuple of what input types it should have. So here it's just a vector of int. and I look through it, we can see we get these type of instructions that are, this is LLVM code, and it has these 4x times I64. So this is LLVM notation for a vector, and this typically means that in the end it will generate vectorized instruction or SIMD instructions from this. So it has this type of shape where it gives the operation, here's an add, and it gives the data type. So here's a 4 wide vector of int64s. And then if you want to see the actual assembly instructions that will be executed, we do code native instead. And then we can see here that the compiler has generated 4 vectorized add instructions here, and it's operating on these YMM registers, which are these different registers have different names, and the YMM registers are for SIMD. They store 256 bits, and then AVX 512 has something called ZMM, which store 512 bits, and SSE2 have XMM registers, which stores 128 bits. But that's sort of a way to checking if your code end up actually using SIMD. And one pretty interesting site, and it's very worth visiting when we talk about SIMD, is the Intel Intrinsics Guide. Go there and try to show a little bit from it. So what it has here, it has basically all the instruction sets. You can see here we have SSE, we have AVX, AVX2, AVX 512, but there's also many in between. There's also different categories. So here we can, if we want to look at all the bit manipulations in intrinsics, we can go here. And if you want to look at, for example, AVX2, it's here. And if you click on a specific intrinsics, you can see things as, this is written from a C point of view. So I'm going to zoom in a little bit. You can see what header file you need to include. You can see the name of the instruction. It also provides a short description and some pseudocode. And then here it gives some performance characteristics. So there's typically given us one latency number and one throughput number. And the latency is basically how long time it takes to get the result after the CPU has started executing that instructions. So, and the throughput is sort of how many you can do, how many clocks per instruction it takes to do this thing. And as you can see here, if I click here, there is a lot of instructions. So yeah, but you can search around in here and so on. So this is a very useful site. And I will show a little bit more how you can use this site from Julia. But yeah, I think I described these different things. So that site is worth mentioning. So that was just a little bit about SIMD in general. So now I want to talk a little bit like, okay, like SIMD, I want to use it and I use Julia. So how do I get access to this stuff? So the first thing is to do nothing. Because a lot of operation in Julia already uses SIMD. So for example, broadcasting, when you write this type of operation, it will use SIMD when possible, sort of under the hood. You don't have to do anything special. When you write reductions, like a sum or minimum and so on, SIMD will be used. And many packages have structured the code so that SIMD will be taken advantage of. So here I have an example from static arrays, which is a very good package if you're dealing with matrices or vectors which are kind of small, maybe smaller than 8 or something like that. So here I create a static matrix, which are known from the compiler's point of view, known size 4x4, and a matrix here. And I look at the LVM when I do a matrix times vector operation, and we can see here we get these 4x double here. So these are SIMD instructions being used inside this matrix multiplication. So that's pretty nice. Many, like a lot of your code probably uses SIMD already without having to do anything. And the second thing is, just by writing your own normal code, Julia's compiler and the compiler library it uses, which is called LLVM, has ways of looking at the code and transforming it into vectorized or SIMD code. So here I wrote the simplest possible sum function, I would say, just initialize s to 0, do a loop over the vector, add it, and then return the value. And I look at LVM when I insert the vector here, and you can see there is SIMD instructions in here. And that is sort of the loop vectorizers that does something here. It transforms a loop into using SIMD instructions. And the second one is another type of auto vectorization. So here I have a function a comma b, and I do this element-wise addition here and generate a tuple. And when I pass in 2 tuples here, it figures out that it can do these 4 additions in one go, and it generates one of these add instructions here with the 4xi64. And there's no loop in here, so this is something called the SLP vectorizer that does this. So it looks at sort of scalar code and sees patterns and figure out, okay, but these things I can actually just load these separately and do the addition. So there's 2 parts to this auto vectorization. So here it's useful to talk about some performance annotations that might be required. So if I go back, and here I executed this mySum on a vector of integers here. But let's try run this on a vector of floats instead. So I load this package called benchmark tools, which is that makes it easy to benchmark, create some random data, and I look at performance for mySum when I put in this random data, which is floating point numbers in here now. And if we compare it to the sum function, you see that it's way worse than the built-in sum function, even though we just wrote this loop here that's supposed to do it, and it seems we got SIMD for integers. So what's the difference between integers and floating point numbers? Well, if you look at addition with floating point numbers, it's not associative. So what that means is that depends where you put the parentheses. If you have A, B, C, D here, where you put the parentheses, you will get different results with floating point numbers. And an optimizer is only allowed to do transformation that does not change the result at all. So if it would do the SIMD transformation and sort of add things in different order, you will get a slightly different result, but it wouldn't be exactly the same. And therefore, an optimizer is not allowed to do it. So in Julia, there's this add SIMD macro, which you can put on a loop, and it basically tells the optimizer, like, okay, if you want to reorder things and get a slightly different answer, it's okay, because I put this explicitly here. So the only thing I changed in this function now is I put the add SIMD here, and it tells the compiler, okay, you are free to do some reorderings. And now when I look at the benchmark here, you can see it goes to the value pretty close to the sum function. So this SIMD is useful to put on loops when you need to allow the compiler to do these reassociation of floating point arithmetic. Another thing that's quite important is that if you have bounds checking, if you have do some bounds operation inside a loop, then that will typically disable SIMD, because basically if you had a bounds error, the function will error there, and it would have, in order to not change the result, it has to error exactly at that point. So therefore, the optimizer cannot really reorder things. These bounds errors sort of synchronizing, or it puts a lot of constraints on what can be done. So then you would need to use this inbound macro on index operations to say that, I'm sure that this will be in bounds and you don't have to check it. So typically what you do is you check the indices before the loop and make sure that everything's okay. And then inside the loop, you turn off bound checking with this macro. In this case, I don't need to turn any bound checking off. I'm not doing any indexing, and the compiler is smart enough to realize that this will never be any out of bounds when I just write a for loop like this over a vector. But in some cases where you explicitly indexing values in a vector, you might need to use it. So the third way is to use a package called SIMD.jl, which is a library for doing SIMD operations. So what you do is that you just load the SIMD package here, and then it gives you access to this vec type. And a vec type you can sort of think about as one of the boxes that I showed in the beginning. It's like a container of numbers. So here I can put 4 integers into this vec type, and then I can just act on this like it was a collection of data which acts element-wise. If I add them, do it like this, or I can add a number to it. And if I look at what happens when I add a number to this type of, I print out the LVM code here. You can see it does an add and a vectorized add instruction. So it takes this 3, it creates a SIMD vector of it, and then it adds that to the other SIMD vector. And so that's one way of using SIMD for like standard math stuff. And it also has some more advanced things. It can do these shuffles, which is you have two vectors here and you want to reorder the data somehow. You can call shuffle vector on these 1, and then you give sort of which values you want. So here it takes 2, 3, 4, 5. So you can think that you put A and B after each other, and then you take value. Here's zero-based indexing. So this is the second value, put it first, third value, and then keep going, fourth value, fifth value, and you get a new one. And from that, it can generate one sort of shuffle vector instruction, which can be quite efficiently used. And if I go to the SIMD library here, just to show it a little bit. So it supports quite a lot pretty much all the standard ones, different. And then, yeah, you can do reduction with it. So if you have a vector of numbers, you can do the sum of it and so on, and reductions. And yeah, it contains quite a lot of stuff. So that is one way of using SIMD in Julia. And one thing that's quite important is that if you use SIMD.jl, the library, it is generic, sort of. You're not putting an assumption about what computer the code will run on. Depending on the CPU the computer has, the different code will be generated. So it's not really a one-to-one correspondence with CPU instructions here. And this is up to LLVM to then take these sort of higher level code and compile it down to suitable machine code. So as an example here, let's say I have a vector of 7 numbers. There's no instruction set that has exactly this vector size. So you can't really map this directly to an instruction, but still I can do v plus v, and I can take the sum and so on. And when we look at the code native here, we can see that it does some quite complicated stuff here, because since we don't have an sort of even multiple of the size, it needs to do some trickery. But depending then on what works best on this machine, it will generate different things here. But the fact that the code generated is generic is quite useful, because then you can only sort of write it once, and yeah. But sometimes what can happen is that this code here becomes a bit complicated. It's always worth checking that in benchmarking if this code actually becomes faster than the serial version. Maybe your code is not very useful to run SIMD on, so it's always good to benchmark. So I forgot to look at the chat, and I guess we said it should be interactive, so maybe I'll go through some questions now. So one question have to be true. Does Julia automatically make use of AVX512? It's available on the running processor. And yes, it will use AVX512 if it's available on the running processor. Like LLVM will look at the processor and compile things to the best it can towards the exact architecture it runs on. And then the question is, does it have to be tuples? I guess when I show that example, when you add two tuples, it uses SIMD instructions, and it doesn't. Let's say you have two vectors instead, and you add them. You will probably use SIMD instructions then as well. But when you add two vectors, it's going to be a loop running there, right? Because it doesn't know how big the size of the vectors during compile time. But with tuples, it knows the size during compile time, so that's why you can generate more efficient code for that. Then there's a question if the core matrix operation like mul already exploit SIMD well. And for Julia, when you call mul bang or when you call matrix multiplication, it will end up in a BLAS library like OpenBLAS, or you can also load the MKL library to use MKL. And they are very hand-tuned libraries to run the matrix multiplication as fast as possible. And they will sort of have written these manually assembly code, which will use a lot of SIMD. Yes. So yeah, matrix multiplication will end up using SIMD. And then there's a question if you can make SIMD behavior the default, maybe a command line flag. What you can do is you can set the math mode to fast, and that basically turns off a lot of these more strict math things. I would not recommend that because it sort of breaks a lot of assumptions people make about what will happen when they write code. Some code might rely on the math mode being the way it is, sort of, and turning that off is usually not a good idea. So I would be more selective and see where it matters. You can put SIMD, and where it doesn't matter, you can just leave it off. And then there's a question of if there's any overhead introduced by the manipulation of data when using SIMD.jl. Well, it shouldn't be in SIMD because I mean the overhead might be compile time and so on, but if you use it correctly, then it should just compile down to pure assembly code. Like if I go back, see if I go here, if we look at the LLVM here, it just becomes very short, and if we look at the native, it would just be one instruction, so that, or a few instructions. It wouldn't be really any overhead when it comes to runtime like that. And then there's questions about what are good ways to contribute to SIMD.jl. Need to think a little bit. I'm not 100% sure what the stuff, what's left to do there, but basically SIMD.jl looks at the LLVM intrinsics and try to have a corresponding nice way of doing that in Julia. So if there's things that are missed there, that could be one way. And then there's a question, how much these approaches add latency. I mean, that's hard to say a real number on. It depends a little bit on exactly how much you use and so on, but I guess we could time loading SIMD. It was less than 0.1 seconds, so at least loading the package was quick. But then there might be some overhead when you're using it as well. I don't have any actual numbers on that. So I'll continue now, see where I was. Okay. So another way of using SIMD is to directly call intrinsics using LLVM calls. So here we go back to this big intrinsic Intel intrinsic page that I showed earlier that had all these intrinsics in it. And if we look at one of these, let's say this AES stick that does one round of AES decryption, and it has this instruction AES decryption. And let's say we want to use this one in Julia. How would we do it? We can look a little bit on this one here. So it has this __M128I. What it basically means is a 128-bit integer data thing. And it takes two of those as input, and it returns one of those as output. The problem here is that this doesn't really contain enough information to call this from Julia, because Julia, this is written from a C point of view, but Julia sort of uses LLM, so we have to sort of figure out a way to find the information we need. So one way I've found out that you can do it is to use this site called Godbolt. You can also just use a local compiler, but it's easy to show using the site. And I can click on it, and hopefully it will show up here. So what I basically did here is that I just did the simplest possible C program that calls this intrinsic, and I include this header, and then I ask it to write out the LLVM code. In the LLVM code, we can see that this is the LLVM name of the function. So this is sort of the secret name that we were looking for, and also what data type ends up actually calling out. So here it turns that M128, it turns into 2 times I64. So that's what I have here. So what we do then in Julia is to sort of translate this. So we translate this underscore M128I into a tuple of 2 I64s. And then this is sort of the magic C call, where we put in the name in LLVM form of the function. And we do a C call, and we write LLVM call here. This is the output. These are the input types, output types, input types. These are the input values here, the function. And then I call this function with 2 of these values, and I look at the native one. I exactly have this VES deck here, which is exactly the instruction I wanted. But you can see here in the name here, it has an x86 and it has this AS here. So this is not a generic code anymore. Like if you would run this on a CPU that doesn't have this specific instruction, it would probably crash, saying that it couldn't find this instruction. So now you have to either, if you do stuff like this, you have to sort of either limit the sort of computers that you say that you're going to run on, or you have to have some kind of backup if it doesn't exist and so on. So this is more trickier, I would say. But if you need access to these very specific instructions, then maybe this would be your only chance of that. But there's some drawbacks to doing this. So to give a little bit of summary, SIMD in general has some great potential performance gains, as you could see, but it can be a little bit tricky to get full use out of it. Maybe you need some performance annotations, maybe you need to think about how your data is stored and so on. And if you want to use SIMD in Julia, I showed a few different ways of beginning from the very easy things to the harder things, is to just use the standard library, which already includes SIMD. If you just write normal code or use packages, the packages might have made sure that SIMD is used, or the normal code, the auto-vectorization might kick in for the normal code. You can use simd.jl, which is a package to do SIMD in Julia. Or finally, the sort of most hardest and low-level thing is to use these intrinsics with LLVM call, which I would say is the last option. But if you really need a specific one, like the AES decryption or something similar to that, then you could do that. I put a bit of references here to different packages or different blogs and so on, just a little bit. I will go to the slide link soon, so you don't have to take a screenshot or anything, but that's it. Thank you very much. I will go to the first slide, which contains the link to the slides. So let's go back. And then if you look down here to the right, I did this shortening link here. So I'm just gonna put that. No. Shouldn't have zoomed in. Okay, I think it's big enough for you to see. So that's the link to the slides if you're interested, and that's it from me. Let's look at the chat if there's anything more here. I don't think there's any more questions. Miguel posted the link to the slides in the chat. That was a very good idea. I should have done that too. So I'll hang around a little bit, see if there's any more questions, but otherwise, thanks for joining and good luck with your SIMDing, future SIMDing.
Thank you very much, Christopher. That's an excellent presentation, and thanks for doing that on the ready, if you will, having issues with the Zoom. But for the recorded version of this presentation and our past webinars, you can visit the resources tab at juliacomputing.com. For any help with your existing Julia use case or upcoming Julia project, please reach out to us at sales@juliacomputing.com, and we'll be happy to help. Thanks again, everyone, and have a great remainder of your week. Thanks a lot, Christopher. Appreciate it.
Yeah, there's one more question here, so I will just answer.
Go ahead.
And the question is if SIMD works on CPUs only, or will it work, for instance, running Julia code on a GPU? And that's a good question. I'm not sure what happens if you write a code that uses simd.jl and then put in like GPU arrays on it. That would be interesting to try. Might work. I can't really try it here on my laptop because it's a Mac laptop and I don't have CUDA and so on installed. So I'm not sure actually, but because GPU has a completely different set of instructions and so on. So you would have to try it and write a kernel using simd.jl and see if it works. It's possible, but I'm not sure. Okay, I think that's it. I'll stop sharing.
Thanks again, Christopher. Thank you very much. Thanks, everyone, for joining us. Appreciate it.